Welcome to the third lecture in this series. So, we will talk about hardware architectures, and hardware architectures are very important because they capture the degree of reuse, right? So, they capture the degree of reuse, they are the reason for the prevalence and prominence of CNNs. The reason being that the maths was established long back, it was established in the 80s and 90s. But the reason that they are so prevalent as of today is because we have the hardware, right? So we should never forget that fact that hardware is the most important. So of course, as we have discussed, there could be two kinds of reuse. We could have temporal reuse, where because of stationarity we keep on reusing the same data. So we keep reusing it as much as possible. Then of course spatial reuse, which basically means that if let's say we have computed something, so then we kind of pass that semi partially computed value between different p's of the accelerator, and finally once it is fully computed we send it back. So a naive algorithm would be that we get something and then we write it to memory, again we read it back, compute, write it to memory, so on and so forth. But if I want to reuse it spatially, what I do is that I read it once, do as much as I can with it, and then write it back. So here also we'll use the same notion that we used for software, which was in the previous section. But of course here what we will do is that we may slightly change the ordering of the loops to make it more hardware friendly. But note that our notion is not, it doesn't capture everything, right? It's not that using our notation you can exactly design hardware, so you would need more things. It is representational, it holds more for software than hardware, but still it gives you an idea how is it that I would like to do the computation. So as I said, the disclaimer is that for hardware the notation is not complete. It may not capture all aspects of the data flow. So that should be kept in mind. So what we will do is we will look at two different methods of transferring data in hardware. One is broadcast. So which is where I send a value to all the P's in the same cycle, right? So we are thinking of an accelerator to broadly be an array of P's. So if this is an accelerator, we are assuming that there are a lot of P's inside it. It's like a large 2D array of P's. Needless to say, easy to implement, but it's quite hard to guarantee that we are having good timing, because it's a large accelerator and you need to ensure that the data reaches all the P's at the same point of time, and that is going to be hard. So there might be a small amount of clock skew. Clock skew basically means that the clock arrives at different points of time in the individual P's, which may affect the timing. So if I were to look at the timing, then I would kind of like put a big exclamation mark over here, saying that look, don't do that. Instead, try to minimize the clock skew, use the same clock. No one is stopping you from doing that. But what you would do is that whenever you have a clock cycle boundary, a negative edge, you send the data to a neighboring P and don't broadcast. So if you have a neighboring P, you send the data to it. Let it do something with it and then send the data either down or to its neighbor, right? Either downward neighbor or rightward neighbor, so on and so forth. So in this case, you don't require tight synchronization. And what you will be able to do is that even if, the slight issues with the clock, you will still be able to manage that. And it's a far more scalable design. Keeping this in mind, let's take a look at our weight stationary architecture. So if you would recall from when we were discussing these notations, right, way back from there, so it was broadly looking like this, where we go image wise, output channel wise, of course in parallel, input channel wise in parallel, right? And then rows, columns, and then the filters. So what we can do is, if I were to realize this in hardware, what I would do is that I would create an array of P's where the blue part over here is a local buffer, and we are assuming in this case that data is flowing along both the rows and the columns, right? Both the rows and columns. But we will have an additional arrow column wise which indicates two things, which will gradually become clear to you what how we differentiate between the two scenarios. So in this case, what we are doing is that for a given image, we are parallelizing the output channel. So what we are ending up doing is that we are dedicating a column of P's to each output channel. So as you can see, they are connected, right? All of them are connected, but the transfer is happening from P to P. So of course, one way of doing that would be that instead of a single wire, we show a connection from here to here and then a connection from here to here. So, well, that could be done, but that would again be a very, a very minute small detail. It is a better idea to have, think about this conceptually. So to have arrows between one P, the next one, this P and the next one, so on and so forth. So this would be a true systolic transfer. So what happens in this case is that since we are parallelizing this channel wise, the data for different channels, the matrices, right, for the different channels, they arrive row wise. So C1, C2, C3, C4, and the filter weights are already cached within the local buffer over here. So that is why it's a weight stationary or a filter stationary architecture. So I repeat, because it's a weight stationary architecture, the weights are cached here. So then the job of each PE is to take in input data, compute a convolution with the weights here. That would create a partial sum, partially computed data. So basically the final output is a sum of all of that partially computed data. So what would happen is that the partially computed data would flow from this P to the next P. Then it will basically, let's say if x is coming and this has computed y, then what will go here is x plus y. If this has computed z, what will go is x plus y plus z. So if basically every P will take what it is getting from the top, add it to its local convolved output and then send the sum downwards. So the final answer would basically be the value of the first OF map K1. Similar would happen for K2. So of course, every filter, every local buffer over here would store the filter corresponding to the unique input output pair. So in this case, it is C3 and K2. That is the unique input output pair for which the filter is being stored. So then every channel over here, every output channel over here will correspond to a column and the values will be computed like this and like this. So this is a true systolic computation because the input values are coming row wise. The filters are cached in the local buffers of the P's, respective P's, and finally an output is being computed. So as you can see, there are 4 phases in this computation, which is a representative computation with systolic arrays where you are loading the filter weights in each P from the global buffer. GB is global buffer. A block of pixels are being sent along each row, which are IFMAP pixels. Each P is computing its local convolution. And then, as we said, we are adding the values produced by each column. So here of course there are two options. One is the systolic addition, other is that because additions are being done in parallel, you kind of have a tree of adders and that does the job of addition. Of course that is kind of breaks this regular structure. So the tree of adders is not a great idea, but it's again not a very uncommon idea. So you could either have, as I said, a systolic transfer or a tree of adders for doing it. Even though I personally would like to argue against anything that breaks the regularity of a systolic array, And you may want to argue that addition is a parallel process. So why should I kind of sequentialize it? But then I will say that, look, at the same time you can do other work. How to do that we will discuss slightly later. But again, having a regular structure keeps things simple. If I were to look at the input stationary architecture, that would look slightly differently, at least the way we have been presenting it. Again, go image wise. Look at essentially a chunk, a block of pixels, right? Then for a given output channel, what you do is that you keep the entire chunk cached, right, for all the input channels. So basically this would keep a chunk cached for all the input channels, right? And then what you would do is that you broadcast the filter weights, all right? So basically you just broadcast the filter weights. So the filter weights are broadcast to each and every PE. Once that happens, each and every PE computes its respective convolutions, okay? And once the respective convolutions are computed, then they are streamed out via these columns. So we stream the output and the output corresponds to the output channels. So in this case, what is happening is that we are taking a large image, we're kind of breaking that into chunks, right? And then basically, let's say each chunk, of course, it will not be one, because what normally happens is that we have multiple IF maps and these IF maps are kind of fed into one CNN layer, right? So for each IF map, you are taking the corresponding chunk and you're kind of storing all of these, this, all of these in the same PE. So then what you do is that you compute all the outputs for one output channel, all the output chunk values for one output channel, let's say K1. Once K1 is fully done, you move to K2, so on and so forth. So the filter, as we have seen, is a function of the input channel number and the output channel number. So at least for a large part of the computation, the output channel number is fixed, right? So because we fully finish one output channel and move to the next, as this particular construct would suggest. So what happens is that we look at an area and different areas are cached in different local buffers corresponding to different input channels. Then we just broadcast all the filters corresponding to, let's say if you have fixed the output channel, then for each input channel we just broadcast the filters. All of them locally compute their convolutions, keep the partially computed results with them, and then finally they have the output, right? The value for the output channel, at least for the particular chunk that they are interested in, that is available. Then all of that is kind of streamed out to this common output line, and the final OF map is created and it is written to memory. So this is one of the ways of realizing input stationarity. I would say it is not the best way, in the sense there are better possible methods. But as we have said, our job is not to teach the best possible method. There are a lot of tools, notably time loop, to investigate this. It essentially looks at a large number of different combinations and finds the best one for you. So that's not really our aim here, but our aim here is to look at simple representative examples, as we have just seen, where in this case the filter we broadcast and input we keep stationary. Similarly, what we could do is we could have a different IS architecture, where again we go image wise, we look at a chunk. In this case, what we do is that we parallelize this based on the input channel. We consider output sequentially, which anyway we were doing earlier also. And then we keep, for a given input channel, we keep a chunk stationary. So let's see if this is input channel C1. So what we do is that we keep a chunk stationary over here. So just read this, it's pre-filled inputs for a single IF map tile. So for a single tile, we kind of keep it stationary like this. So then what happens is that the filter weights for a given output channel K are broadcast like this corresponding to channel C1, C2, C3 and C4. So what will happen basically is that the filter weights will go here and then we'll compute the convolutions. Then for a given chunk, right, what will happen is that because they correspond to different channels and they have all been convolved with the respective filter weights, the value of the output is nothing but a sum of this plus this plus this plus this, which is similar to the earlier weight stationary or filter stationary architecture that we had, where basically each of the P's was computing a partial sum and the final result was a sum of these individual partial sums. So here also we are doing the same. So what are we doing? Let's say for a given chunk of an image, we will have part of it in C1, then same chunk in C2, same in C3. We will kind of convolve it with, let's say, the filter C1k, right, a function of C2k and C3k, right. So we will convolve these with these. So what we do is that we keep the respective inputs stationary here in the local buffers. We send these filters down here. So what happens is for a given input region, the different partial sums are computed, which is like this kind of convolved with this convolved with this. And the final output is nothing but the sum of these, right? So this sum is achieved via the systolic addition. So the final output comes out at the end. So I do understand that this may be a kind of a difficult thing for many people to visualize, right? Mainly because there are a lot of interconnected concepts and you will have to go back to our previous lecture, which was lecture number 2, to understand the maths behind the CNN, the master equation, and how we arrived from there to this equation. So we have actually come a long way, and I would not blame anyone if you are not able to understand what I am saying right now. So what you should do is read the book. So the book, as I said, is available freely in at least a preprint readable version, and look at that, look at the previous 2 videos in this slide, and then you can come back to this point. So here the key idea is, as opposed to a broadcast, we are using a systolic addition to compute the output. Now let's look at the OS architecture. So in the OS architecture, what we do is we store one OF map corresponding to a given HW region, right, corresponding to an H dash W dash tile, right. We are kind of storing it one in each local buffer. So then what we do is we stream the inputs for the same coordinates, for the same H1 W1 coordinates. What we will have is, for the different input channels, we will have different matrices, right. So basically if we have, capital C channels, then we will have capital C matrices which are streamed one after the other this way. And similarly, the filters are also streamed downwards, where the filter for a column corresponds to a given output, a given output channel. So in this case, what we are doing is that we are in parallel dividing the tiles among the P's, parallelizing the output channels. So we can see one column for K1, one for K2, one for K3, one for K4. Then sequentially we are reading the capital C channels, which we are doing this way, and they are colliding at the right time with the filters in each of these P's. Once that is done, all that we do is we achieve a systolic transfer, right. So they are colliding and then we kind of read the values out via the columns. So in this case, there is no great systolic transfer, because the output, the partially computed output, stays here, the input gets streamed, the filter gets streamed, right, the filters get streamed, I'm sorry, then they collide here, the output is computed, so they don't remain here, but they kind of get streamed through the bottom and they get written to memory. So I deliberately went slightly fast because I'm assuming that you have understood the previous few slides. In case you haven't, then the first 2 lectures should be looked at more thoroughly before you come here, right, because they establish the maths and our notation. And clearly here we are sending capital C tiles via each route, because it's a single tile, but there are capital C tiles because we have that many input channels. So they are coming one after the other via this route. So last but not least, the row stationary architecture, which is also the simplest. So this is super easy. So what we do is we take a row of the input, a row of the filter, row of the input, row of the filter. So let's say that our filter has 3 rows, 3 cross 3 filters. So we take a long input and we take a small filter. Again 3 rows. So our job is to convolve H1 with R1, H2 with R2, H3 with R3. So we do that. Then what we do is we slide the filter down and we convolve H2 with R1, H3 with R2, H4 with R3. Again we slide it down and we convolve. So we have the results of 3 different convolutions over here. Again, understanding this should not be a big deal if you have understood the original equation. So the arrangement of data here can be represented as a matrix as H1, H2, H3, H2, H3, H4, H3, H4, H5. As you can see, H1, 2, 3, 2, 3, 4, 3, 4, 5. So then what we do is in the next cycle, once we have done processing this matrix, we again reload rows from the input. So we have H4, H5, H6, H5, H6, H7, H6, H7, H8, and we keep doing the same convolutions over and over and over again. So of course this process is being done with a single filter, but if you have multiple filters, then the computation has to be done for every channel filter pair, right? So that has to be done. Once we have done this for every IF map, OF map pair, which can be achieved with many parallel units, and of course, we'll have a lot of P's, parallel units, and a complicated dispatcher. So once all of this is done, we'll be able to compute all our OF maps. So this was simple. And the RS architecture of the full system, again, if I were to show you, would be the same where I go image wise, I parallelize it based on the KC pair, output channel, input channel pair. And then what I do is I parallelize the row space. For every row, I compute a convolution. If you can think about it, we can also cache the filters also, right? So basically we can kind of extend this over here. So the choice is ours. I'm not, dictating more than that. But if I were to quickly just do a read through this, so it would basically be that I first parallelize on the basis of input-output channels, then on the basis of filters and IF map rows, and in each P, I essentially need to compute a set of 1D convolutions, which is nothing but a long IF map row and a short filter row. So I need to compute a set of long 1D convolutions, right? So we need a bunch of many of these 1D convolution units. So once that has been done, we are left with only one choice, which is not to reuse anything at all. So not reusing anything at all is an option. It's called no local reuse or NLR. So in this case, what I'm doing is, it's a simple diagram. Let's understand this. I go image wise, output channel wise, input channel wise. So of course I parallelize the input channels. And so then I have multiple input channels. For each one of them, I essentially stream in data, stream in filter data, and I'm done. How do I achieve this in practice? Well, in practice for a given image, what I do is that I send C1, and then basically that is the image data. Then I send the filters also for a certain output channel. I convolve it. At the same time, I convolve NC2 with FKC2, right? I achieve this convolution as well, right? So maybe we'll just fix this. And so the key idea is that I'm doing this convolution, at the same time I'm doing this, at the same time I'm doing this. So all that I do is I do a systolic addition across the P's on the same row. So in the same row, I just do a systolic addition, which is all that I need to do. So we simultaneously compute the convolutions for each input channel and we just add them in a systolic fashion, which is all that I need to do, right? So I am not doing any reuse, any great amount of reuse. I'm just adding them, that's all, and then I forget it. So we have now reached an interesting point where we have covered the space of CNN architectures. So as I said, as of today, the most popular tool for architecture exploration, CNN architecture exploration, is time loop. So you can take a look at it. As far as I know, it is freely downloadable and available. So now we will look at what is it that happens inside a P. How do you compute these convolutions? Because the crux is basically take a 2D region and take a filter and you convolve them, which of course can devolve to something simpler. As a kernel, you take a 1D row, you take a smaller 1D row of a filter and create a 2D convolution out of a bunch of 1D convolutions. So that again is a possibility which we will look at. Let us now look at 1D convolutions. So the main aim of looking at 1D convolutions is that if we can design efficient hardware for implementing 1D convolutions, then we can reuse the same hardware and create a 2D convolution hardware, which is trivial, it's not very difficult. And the heart of the 1D convolution is again very simple, we have seen this several times, which is that for all I compute yi is equal to essentially sum of products, n products. So I basically, for every filter weight from the 0th to the n minus 1th filter weight, I multiply with xi plus j, where this and this are one dimensional arrays. And with that I get yi. So of course, towards the end you need to take care of halo pixels and so on. So we have seen that. So the key idea is that if this is x and then we kind of want to compute a convolution in this range, then there will be some of these pixels which are not in the range. So we assume that they are 0. So the key idea here is that we want to design a theory or design a theory for constructing efficient hardware where this can furthermore be used for creating larger primitives, 2D convolution, 3D convolution, so on and so forth. So if I were to visualize the process of convolution, it would be basically a sliding window over here where X is a one-dimensional array, W is a one-dimensional array. So what we do is that we convolve it with the first location here. So this is Y1. We again move this over here. Again, this is Y2. Again, this is Y3. So on and so forth. For every step, it's a pointwise multiplication and then we are adding all the partial products to come up with the final result, right? So what I can do is that the same thing that I did over here, I'll create what is called a semi-systolic array. So what is a systolic array and a semi-systolic array? Let's keep this for a later point of time when we will discuss what these are. But the key idea is that what I would like to essentially do is that I would like to create a basic element, right, where this is a register. And this element over here is a multiplier which is doing two things, right? So this is not a normal multiplier, but it's a slightly special multiplier in the sense it's multiplying, no doubt. But it is also propagating the value of x towards the right, right? So there's a propagation part and there is a multiplication part. So what we do is that if I look at these four units, we permanently store W1, W2, W3 and W4, assuming that W is a 4-element one-dimensional array, right? So 3, 4, 5, 6, 7 doesn't matter. So we have of course discussed odd number sized filters earlier, but again, as I said, that's not important. So here what we do is that I keep this here. So if you see the values keep flowing in from the left hand side towards the right. The moment x1 approaches, all that we do is we multiply, send w1 times x1 over here, send w3 times x3 over here, this over here, so on and so forth. And here we have a quick tree of adders. So because you could have 4 of these W's or 5, 6, 7, 10, whatever. So the tree of these adders will essentially take all of these values and add them up quickly in a tree-like fashion, and that would be the final output, in this case y1. So this would happen in the first time step. In the second time step, all the values will flow to the right, right? One step to the right, because this is in a register. So the next cycle, this will go here, and this of course will go out, and x3 will come here. So what we would end up doing is we would end up computing this result over here. The result over here is nothing but the value y2, because we are convolving w1 with x2, w2 with x3, so on and so forth. So we are essentially doing y2. So of course here you would notice we are starting the count from 1 to make our life slightly easier, right? So this again is a little bit of liberty that is being taken over here, right? Computer scientists won't like it, but we are taking this liberty for the ease of explanation. Similarly, we compute y3, so on and so forth. So basically the final values come out of this tree of adders, and this tree of adders is on a critical path, because if you think about it, this is a very fast unit, this is a very fast unit, but the tree of adders, depending upon how large is the filter size, this could be the bottleneck. So this is something that we are in principle not very happy with. So the problems, as I said, with the design is nothing but the tree of adders, which is the problem. So this will unnecessarily, it will make the pipeline stages kind of unbalanced and increase the clock period. Unless, of course, we decide to pipeline the tree of adders, which we can. So what we can do is that we can add registers or flip-flops in the middle, like here, one layer here, here, and so on. Can be done, but it turns out that there are better ways of doing it. But let's first look at one more idea for a semi-systolic architecture, which is to broadcast the weights. So in this case, what we do is that we basically send all our inputs. So this would have x1, x2, x3, x4, x5, etc. And what we would do is that we would broadcast w1 first. So this would compute w1 into x1 and store it here. Then you do w2 x2. So then the next cycle it would compute y1 plus equal to, right? Plus equal to being the most important, w2 into x2, so on and so forth. Once y1 has been computed, you get the result which you can read out, y2 you can read out, y3, y4, y5, etc. and then y6. So 6 results you can read out at the same time. And then again you read 6 more at the same time, so on and so forth. Right? So this is the key, this is the big broad idea of doing this. So here of course broadcast is involved, and again we are not happy with the broadcast mechanism, because what will happen is that it's the same wire, right? So same wire is like one long wire connected to both here, 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 and so on. It will have a massive RC delay, because there will be some capacitance over here, some over here. All of that is in parallel, so it will add up. So essentially charging the entire wire will take quite some time. So again, we are not very happy with this design, but this is still a valid alternative design. So in this case, by broadcasting rates, we can still get our job done. So what are the pros and cons of this design? That we either have a costly tree of adders or we broadcast. It will work in parallel. So the broadcasting process itself may have a large RC delay. So we don't like, these parallel wires like this. Not a good idea. We don't like it. We also don't like an adder tree. So again, both take a lot of time and they kind of, imbalance our pipeline. So what we would want is that we would want a systolic architecture that does not have these structures. And between any two combinational units, there is no direct connection. In this case, there was. So these adders were connected to each other directly. Right? So what we would want is that between any two combinational units, so let's say adders, multipliers, whatever, there is always a register. If that's the case, we are happy. And if you would see, that will not imbalance our pipeline, and that is called a systolic array. So the first thing is that can we take one of our previous semi-systolic arrays? So this was, why was it semi-systolic? Well, it's obvious that we kind of have broadcast like connections are semi-systolic by definition, because you can think of this input and this input, they're connected, no register in between. So can we automatically convert a semi-systolic array into a systolic array? So the point is that can we take the previous network and then kind of remove those broadcast connections that we don't seem to be very happy with. So it turns out that we can do something like this. So let's look at it. So what we can basically do is that we can send the weights from the left, we can send the inputs from the right, we can hope or expect that they would collide with each other at exactly the right points of time. And this unit over here will make it more special. So in this case, what will happen is that the weights will keep getting transferred this way. And the inputs, however, will not get transferred this way, they'll get transferred via a register. But again, inputs will go like this. So in this case, what's happening is that the weights are kind of walking through. So this is still not, this is still not a traditional systolic array, but we are getting there. But if you just take a look at it, what you will see is that the weights are kind of getting a walkover, in the sense the W1 weight is still getting broadcasted, right? So we are taking the same old broadcast network, but we have just converted it into a different fashion. And we are searching for an automatic method of converting a semi-systolic array into a systolic array. So what we did is that the earlier broadcast like connection, which was over here, we are still having the same, but we are kind of making it, this is kind of, think of it as an intermediate step before we convert this fully into a systolic array. So in this case, what we are doing is that if you take a look at this unit, let me just clear off the clutter on the slide. The weights are kind of flowing through these units, right? So in this case, in W1, pretty much instantaneously the weights are reaching here, which is nothing but a broadcast connection, right? So you see the weights are flowing, there is no register or clock in between. So instantaneously they flow right till the end. But the inputs are kind of going one step at a time. And the rest of the logic is exactly the same, where you multiply W1 into X1, store it here. Next cycle W2 comes, store it here, so on and so forth. And then, all of them do the same thing. And then, all of them get done at the same point of time. Once they are done, we read them out. And again, we will do Y7, Y8, Y9. So this process will continue. So this is again, so this network, by the way, which is nothing but a kind of a intermediate stage or kind of a rendition of this network, which was a pure broadcast, we converted it to this, and we can clearly see why it is not systolic, because there is a combinational unit here, there is a combinational unit here, which looks like this, and there is no register in between them. So in between them, there is no register at all, and this is what is creating the problem. So if we can kind of convert this to a systolic network, then what will happen is that we will not have these long paths. So designing the hardware will become much easier, because hardware wants balanced pipeline stages. So there is a retiming lemma which will allow us to do this. So sorry, I forgot to mention the title. So the retiming lemma will allow us to convert a semi-systolic array into a systolic array automatically. So let's look at the retiming lemma, and let's take our semi-systolic network which we just designed, which is over here, and let's try to convert that. So what we want to do is we want to create a graph-based representation where the combinational units are the nodes and the nodes are connected by edges. And the weight of each edge represents the number of registers in the node. So in this case, what we are seeing is that if we have this CU and this CU, there is an edge between them whose weight is 1, because there is one register. And again, between these, the weight is 0 because there is a weight. So you can say this is the weight is 1, there is one register, 1, 1, 1, 1, 0, 0, 0, 0. And basically from here to here, there is a graph. and this indicates that it is 1. So what is basically happening is that the weights are flowing, right, and basically inputs are flowing. So we designate one node as the host, which is basically, if you look at this, right, so pretty much you can say that, anywhere that you go, you're finally, kind of coming here, towards the host. So you just create a dummy node called the host, and we will see the dummy node called the host will play a very important role. We will see how. So the properties of such graphs is that in a semi-systolic graph, you will always have some zero weight edges because there will be a pair of CUs or combinational units that don't have a register between them. In systolic networks or systolic graphs, you will never have a zero weight edge, right? So basically what we see here is that, to begin with, we don't have any negative weight edge, right? As a result, there are no negative weight cycles. So we know from, our study of algorithms that whenever you don't have a negative weight edge, it is possible to find shortest paths. Okay. So basically the idea now is that we will use some of these ideas and we will try to convert a semi-systolic graph to a systolic graph using some of the things that I just mentioned, such that we have an alternative graph where every edge has a non-zero weight, which is what we want. So the basic idea of retiming is like this. Let us assume this is a combinational unit and you have edges entering it and you have edges exiting it. So what we will do is that let us say that these edges have some weights. For the sake of simplicity, I have assumed it is 0. So what we can do is we can add a lag of k, which basically means that to all incoming edges I would add k, and to all outgoing edges I would subtract k, right? So then the rest of the world will not be able to make any difference, because any path that is going through this CU, you are adding k, you are subtracting k. So any path that is going here, its path weight remains the same. But in the immediate neighborhood, what you are doing is that you are adding a lag of k, which basically translates to adding k to all the incoming edges and subtracting k from all the outgoing edges, right? So this is the meaning of adding a lag. Similarly, you can add a lead of k, which is the reverse, subtract k here and add k here. Other nodes, needless to say, will not perceive the difference because any path that is traveling through this CU has a plus k and a minus k attached or associated with it. So what is the effect of lags on the edge weight, right? So if I look at the weight of this edge, the new weight of the edge is basically the old weight of the edge plus the lag of the head because you're adding something over here, minus the lag of the tail because you added something here by taking away something from here. So the new weight is the old weight of the edge plus the lag of the head minus the lag of the tail. So the idea is, can we find a lag function, because in this case, as you can see, the rest of the world doesn't care, such that the edge weight of every edge is greater than or equal to 0, right? If we can do that, the resulting network is semi-systolic, right? So for basically, if we can do that, this will be a semi-systolic array. And the point is that if we can somehow kind of add more registers or kind of move the registers, which basically means add a lag such that it is greater than 0 for every edge, it becomes a systolic network, which is what we want, because we do not want two combinational units to be connected together with a wire, right? This is something that we don't want. What we want is that they are always separated by a register. So I had discussed this earlier, but what we could do is that we could take a look at this once again, that if there are no so it's easy to prove that, look, if you are not changing any weights or something, finding a shortest path is always possible because there are no negative weight edges or cycles. So as I said, we will keep on using this result, and we will also use one more result, which is that if there are no zero weight cycles, in the sense you don't have a cycle which is like this, right? There are no zero weight cycles. So basically the thing is that the original network, if it doesn't have a zero weight cycle, then any network where you add these lags will not have a zero weight cycle. So this is something that is there in text on retiming, and it's kind of easy to prove. Let me give a hint of the proof. So the idea is that if you take any cycle and you just add them, then because of this equation over here, the lags will all cancel out, right? So basically if you just go over here, all the lags that you add will cancel out. So the sum of the new weights will be equal to the sum of the old weights, and of course, as I said, this will cancel out in a cycle. So basically the original network didn't have a zero weight cycle. Then the new network, after adding lags, will not have a zero weight cycle. So we'll use this result. Hang on to it. So here are the steps to convert a network into a systolic network given a semi-systolic network, which is the type that we have seen. So what we did is, first we had an approximate network which was like this, had broadcast connections. We converted it to something like this, which is the same thing, still semi-systolic, but we just added the combinational units where the weights kind of pass through. Easier to convert. Converted this to a graph, which is, it would look like this. We added a dummy host node. And then finally we did some proving of some simple theorems. So then we come at so now the idea is that we want to convert the semi-systolic network or the semi-systolic graph. So what we do is, given graph G, we compute G minus 1, which means we subtract 1 from every edge weight. So if edge weight was 0, we make it minus 1. If it's 5, we make it 4, so on and so forth. So let us assume it does not have a negative weight cycle, right? So then I define the lag V, or the lag of a vertex V, as the weight of the shortest path from V to the host in the graph G minus 1. So of course here you will have to take a look at traditional algorithms. So any graph that does not have a negative weight cycle is guaranteed to have a shortest path, which can be found using the Bellman-Ford algorithm. Alright, is guaranteed to have a shortest path. So you find the path from V to the host in the graph G minus 1. So the weight of the edge E, right, basically which is from U to V in G minus 1 is basically the old weight E minus 1. Now what we do is that we have computed a lag function on top of it. And the lag function in this case corresponds to the shortest path, as we have said, the shortest path to the host. So the lag of U is less than or equal to old weight E minus 1 is the weight of the edge in G minus 1 plus lag of V. And so then we basically, from this we get this relationship over here. So proving this is quite simple. So lag of V is basically the weight of the shortest path from V to the host. So basically the shortest path of U will either go via the U to V route or take some other path to the host. So the weight of the path from going from U to V and V to the host is nothing but lag V, which is the shortest path from V, plus old weight E minus 1, because we are computing the shortest paths on G minus 1. So this is the weight of this path, right, the LHS over here. Old weight E minus 1 plus lag V is nothing but the weight of this long path. However, lag of U, which is the shortest path from U, could either be this path or could be some other path. Whatever its weight may be is less than or equal to the weight of this path, which is obvious. This follows from the way that shortest paths are defined, that any path from U to the host is guaranteed to be, its weight is guaranteed to be less than or equal to this path, because otherwise, the thing is that otherwise, this would be the shortest. So either it is this path, in which case there is equality, or another shorter path exists. I can do a little bit of algebra and kind of, arrange these like this. The weight of the new weight of the new weight of the edge is nothing but new weight E is old weight E plus lag V minus lag U, which is something that we have established earlier. And from this equation over here, we see that new weight E is greater than or equal to 1 or greater than 0, which means that the new network is systolic. right? So this is exactly what we wanted to establish. So this basically means that assuming, so we take the graph, we compute the graph g minus 1, and then we compute the shortest paths to the host if there is no negative weight cycle using the Bellman-Ford algorithm. Then what we do is we compute the new weight of each edge as old weight e plus lag v minus lag u, and this is guaranteed to be greater than or equal to 1 given the properties of the shortest paths. And the way that we would actually convert is that we would then add these registers between u and v to make it a systolic network. So let us now consider the other case. What if there is a negative weight cycle in J minus 1? Well, what we need to do now is that we need to slow down the network or create an alternative network which is slower but will not have a negative weight cycle. So what we do is that we create a network Kg, which is nothing but you take each and every edge weight in G and we multiply it by a factor K. And we choose the smallest such case such that Kg minus 1 does not have a negative weight cycle, which means that if G minus 1 has a negative weight cycle, we don't consider it. We consider 2G minus 1. If that has a negative weight cycle, we consider 3G minus 1, so on and so forth. So what's the implication of this? So implication of this is that the moment we multiply a network or its edge weights by a factor of k, it slows down the network. Which means previously if there was one register on an edge, now there will be two registers. Which means that if the delay was 1 cycle, it will become 2 cycles. Effectively, your network gets slowed down by a factor of k, which is something that you may not like. So if I come back to my example, right, and I look at the semi-systolic graph over here, so this would be the graph G, which is our running example, which is the one that we have been considering up till now. If I compute G minus 1, just look at the previous one, I just subtract minus 1 from each, then all the 1's become 0 and all the 0's become minus 1. Unfortunately, there are negative weight cycles like this one, whose weight is minus 1. So I compute 2G minus 1. 2G minus 1, there are no negative weight cycles because this is a 0 weight cycle, but it's not a negative weight cycle. So there are no negative weight cycles. Alright, so this basically means that I am safe because I can work with it because shortest paths are defined. So what I can do is now I can compute the shortest paths to the host. I can annotate each of these nodes with its lag value, compute the lag value of this, and their lags happen to be minus 1, minus 2, minus 3, minus 4, minus 5 and minus 6. So then what I can do is I can do the retiming, which is nothing but new weight is equal to old weight plus lag v minus lag u for an edge that is going from u to v. So in this case, what I would do is that, if you would look at this and so this is the graph 2G minus 1. So if I let's say see this is let's say u and this is v, then lag v minus lag u is actually plus 1. So what I would do is that I would annotate them like this. So if I consider this u and v, then lag v minus lag u is basically minus 1 minus minus 2, which is equal to plus 1. And if I take the old weight, so the old weight of this edge was 0. So the new weight would be 0 plus 1. So then, and similarly, let's say for this one, the new weight would again be different. So I've just shown one example. So then you would find after doing all of this, the new weights would become 2, 2, 2, 2, 2, 1, 1, 1, 1, 1, 1, and so on. So basically, our new network over here has basically it has slowed down. So all the ones, so because we multiplied by 2, our new network did slow down. But what has basically happened is all the ones became 2's. So if I look at these arrows over here, because they started at the same point and ended at the same point, lag u and lag v were the same. So I'll just write this equation once again. New weight E is equal to old weight E plus lag V minus lag U. So if we look at these edges, they start and end at the same place. So lag V minus lag U is 0. But because we multiplied everything by 2, so all the ones which were there, all of these weights became 2. But these were 0 to begin with. So 2 into 0 is 0. But lag V minus lag U was 1. So that's the reason what happened is that all of them became 1. But if you just look at the final state of this network over here, yes, it is slowed down. But the good news is that there is a register or a non-zero edge weight between any two combinational units. So this network is systolic. Alright. So using a retiming theorem, what we have done is that we have converted a semi-systolic network into a systolic network. And how did we do that? Well, so we took the original graph and of course we added our edge weights and a dummy host node and so on. Then we considered the graph G minus 1. If it didn't have a negative weight cycle, we went forward, or we kept on multiplying with a 2, 3, 4, 5 until we reach kg minus 1, smallest value of k, such that it didn't have a negative weight cycle. So all the weights etc. got multiplied. And then what we did is we computed the shortest path of every CU to the host, combinational unit to the host. And then we computed the edge weight, which is old weight E, but old weight E is not for G. The old weight E is for the graph Kg, right? So basically it's a slowed down graph, right? So old weight E is the original weight multiplied with K plus lag V minus lag U. So this ensured, given our retiming lemma and the theorem that we proved, that the edge weights are all greater than or equal to 1. This makes it a systolic network. So if I were to realize this network, so just see this and just see this, you will see both are equivalent. So the idea basically is over here that what I do is that I add a register between these combinational units, a register between this and this, which was not there earlier. Sorry, this was there earlier, but this one was not there. One register between this and this, so there are no more broadcast connections. And then basically there are two registers between the the Y connection that we had. There are two registers. If I kind of go back and show you the network that we had, you would see that we had fewer registers. In this case, we have added more registers, in the sense this has become a roundabout path like this, and there is a new register over here. So coming back to the same point over here, this is what our retiming lemma has given us. And again, the units remain the same. It is just our network has gotten slowed down by a factor of 2. So what we do is we send the weight W1 and then we don't send anything. So this empty square stands for nothing. Again weight W2, then we don't send anything. For the inputs, again we don't send anything, then X4, and then don't send anything, then X5, so on and so forth. There's a gap of essentially 1, such that both of them collide at the right time. The values Y1, Y2, Y3, Y4, etc. are all produced. But again there is a gap. So what we do is, if I take time t equal to 1, the only value I am producing is x1 into w1, right over here. In the next time step, I am producing x2 into w1. In the next time step, I am producing two values, x3 into w1 and x2 into w2. But again, I am doing the addition and I am sending it via these registers. So this is something that someone should look at offline and kind of verify that they agree with me. So by this time W1 would have come here, X4 would have come here, they would collide at exactly the right time instant. So I am doing these computations over here. Finally, I am doing these two, and t is equal to 6, I am doing these. So what's happening is that, it is taking more time. I'm doing exactly the same set of computations, but my throughput has reduced to half. So 50% of the time I'm not doing anything. So if we take a look at this combinational unit, so I'm doing one multiplication, then nothing, then I multiply and add, which is what this is supposed to do. And then I'm doing nothing, then I multiply and add, and then I'm doing nothing. The same is true for the rest of the units. I'm in a sense computing exactly what I was computing earlier, but in this case there is an idle time of 100%, right? So again, we wanted to gain performance by converting a network from semi-systolic to systolic, but we appear to have made a really balanced array with registers and everything. We are happy, very proud of that, but we seem to have lost 50% in terms of performance. So what do we do? So basically what we could do is that we could activate these functional units only when you have valid data. That could save us power. Fine, we can save some power, but what do we do with performance? Well, the idea is that we can increase the performance, but first you consider the original systolic network. So what you can do is that you can perform two separate convolutions in parallel, right? So what you could do is that here you could put another set of weights, or maybe the same set of weights but a different set of data, and here again you could put another set of data and compute two convolutions in parallel. So what would happen is they would not interfere with each other, because as you can see there are these bubbles that are there in the pipeline, right? So in this case you would compute one convolution, and then let's say for another set of data, again compute one more, add a partial sum here, add a partial sum here. So instead of, the idea is that you could still achieve the same throughput, not 50% but 100%, by using these kind of empty cycles and unused cycles in the units by computing another convolution. So that could be a different set of weights and a different set of inputs, or the same set of weights and a different set of inputs, or same set of inputs and a different set of weights. Good. So now by interleaving these two convolutions, we can utilize the idle cycles, and the key point is that our throughput can get bumped from 50 to 100%. So this idea can of course be extended to graphs of the form kg, where k is 2, 3, 4, 5, 6, where we can compute multiple convolutions at the same point of time, and also when we are tiling, or when we are doing multiple 1D convolutions because it's part of a 2D convolution, then of course this can be done quite easily, right? And given the fact that this approach aligns very well with row stationary operations, the row stationary paradigm, a lot of designs are actually using the row stationary paradigm, are using such networks for implementing a row stationary architecture. So 2D convolutions, the idea is the same. What we basically do is that we look at it row wise. So then we convolve rows x1, x2, x3, and then we kind of add them to get the row for y1. Similarly, we look at x2, x3 and x4, again we get y2, same, right? x3, x4, x5, get y3, so on and so forth. Do we have a direct approach for 2D convolution, which again could be slightly wasteful, right? I am not denying that it's not wasteful, but can we have a direct matrix based approach? Because again you need to think about it, that 1D convolution hardware has come now, but for a long time GPUs and other accelerators did have conventional matrix multiplication hardware. So the question is, can that be used? Well, the answer is yes. So we will not use systolic arrays, or we may use systolic arrays for matrix multiplication. But let's look at a different way of doing 2D convolution directly. So in this case, we consider X to be a 2D matrix, W to be a 2D matrix of filter weights. So the crux is to realize 2D convolution using a regular matrix multiplication. And the fact that matrix multiplication is very common, GPUs are optimized to deal with it, and there is also a lot of matrix multiplication hardware, is always good, that even if there is a little bit of wastage in terms of space, we convert this to an equivalent matrix multiplication problem. So what is done here is that a doubly block circulant matrix called X hat is created, where the idea is that you arrange these terms in such a way that the output is nothing but a 2D convolution. So if you can see, what we have done is that we have arrange them in this way such that W11 gets multiplied with this, W12 with this, W21 with X21 and W22 with X22. Then what we do is in the next row we multiply 11 and 12 with these two entries, and then we skip one entry and then again we multiply with these two. So if you just work it out, you will see it is the same as a 2D convolution, exactly the same. And this matrix, it has been created in a special way such that the result of the matrix multiplication is basically the final output of the convolution. So this of course will be a 1D output. So why is that the case? Because this is a 4 cross 8 matrix and this is a 8 cross 1 matrix. So the final output would be 4 cross 1, but that can again be converted to 2D, right? And we can use regular matrix multiplication hardware, super optimized, for realizing this. So this is again one more way of computing 2D convolution, which is to, instead of using a 1D convolution as a basic kernel, we use a matrix multiplier as the basic kernel. So now we are done with this part. So in the next lecture, we'll talk about optimizations and the memory system which is kind of specialized for ML accelerators. We will talk about that.